All right, so we're going to cover in the review section 2.2 and 2.3, and then we'll do 2.4 on Wednesday so that we can start reviewing for the exam, because the exam is going to be a week from this Wednesday. All right, so we're going to first in section 2.2 talk about rounding and significant digits. And rounding is one of those things that I assume you've probably got. Gosh, I don't know, where do you learn how to round off really early on? But it's one of those skills that we somewhat forget how to do it. All right. So significant digits, let's talk about that first. And this book is not particular about you figuring out how many significant digits you need to round to. They pretty much always tell you how many digits to round to. But when you are looking at real world problems, then it is kind of important for you to know from your data how many significant digits you have, so that when you present your data later to your boss, that you round off to an appropriate number of significant digits. All right. In this book, it's common just to round to 3 decimal places. So let's recall what our decimal places mean. So if you have one number to the right of the decimal point, that's the tenths place. If you have 2 numbers to the right of your decimal point, you have hundredths or 0.01. If you have 3 numbers to the right of the decimal, that's the thousandth place. And then 10 thousandths is 4 decimals, 4 numbers to the right of the decimal, etc. Are you still writing? Okay. In some cases, we will be asked to report the functions with 3 or 4 digits of accuracy. These significant digits carry meaning that contributes to the precision of the number. In general, significant digits are those from the first non-zero digit on the left to the last digit after the decimal place, if there is a decimal place. If there's no decimal point, any zeros to the right of the non-zero digits are not significant digits. What do we mean by all that? So if you're looking at significant digits in a number, all non-zero digits are considered significant. All zeros between significant digits are considered significant. For example, if I have the number 1006, the 2 zeros are considered significant because they occur between 2 digits that are significant. So if it's a non-zero number, it is considered significant. And if you have zeros in between, those are also considered significant. So that particular number, 1006, has 4 significant digits. All zeros that are both to the right of the decimal and to the right of all non-zero significant digits are themselves considered significant. So if I write the number 25.00, there's no reason for me to write the 2 zeros to the right of the decimal place unless I'm telling you they're significant. Otherwise, I don't need to write them at all. Leading zeros are not considered significant. So in this number right here, 0.0324, the 0 in front of the 3 is not considered significant. And the reason for that is that you could actually write this using scientific notation. I'm moving the decimal point 2 places to the right. So I'm going to write that 10 to the negative 2 power. So since I can do that, and I better put the 3.24 in there, 3.24. Since I can write it that way, the 0 in front of the 3 is not significant. So it has 3 significant digits. The 3, the 2, and the 4 are considered significant. The same is true for the other two numbers. I could write 56,300 as 5.63, and I'm going to move that decimal point 1, 2, 3, 4 places to the left. So we're going to write that as 10 to the 4th power. And since I can write that in scientific notation as 5.63 times 10 to the 4th, it only has 3 significant digits. The 2 zeros to the right of the 3 are not considered significant. Now the 30.0, because I put that 0 to the right of the decimal place, I am telling you it's significant. So in that case, that has 3 significant digits because I wouldn't write that 0 there unless I'm telling you it's significant. And why do we write decimal places so that we imply significance? Well, it's the way we measure, the way we take data. So suppose you measure your weight to be 132 pounds on a scale that can be read only to the nearest pound. Well, then it would be misleading for me to say I weigh 132.0 pounds. If the scale can only measure to the nearest pound, I would not put any decimal places to the right, any zeros to the right of the decimal place. So if I say I weigh 132.00, unless the scale measures to the nearest hundredth of a pound, then I'm being misleading as to the accuracy of that measurement. So 132 has 3 significant digits. It implies the measurement is accurate to the nearest pound, while 132.00 has 5 significant digits and implies the measurement is accurate to the nearest hundredth. So it's one of those things, just adding zeros to the right of the decimal place is incorrect because you're implying accuracy to your answer that's not actually there. Note that zeros are significant when they represent actual measurements, but not when they serve only to locate the decimal place. We assume that the zeros in the 132.00 are significant because they wouldn't be there unless they were. In contrast, the number 600, the 2 zeros are not significant because I could write that number as 6 times 10 to the 2. Or, for example, if that represents centimeters, 600 centimeters converted to meters would be 6 meters. So 600 centimeters is equal to 6 meters. And again, the zeros are not significant. For example, determine the number of significant digits in the given approximate numbers. How many significant digits do you have? 6. Each of these numbers is significant, including the 0. The 0 occurs between a 4 and a 4, so it is significant. How many significant digits do you have? 2. Why is it 2? because it's not in the middle, exactly correct. So the zeros are to the right of the 2 and in front of the decimal. So those are not considered significant digits. You could also write this as 6.2 times 10 to the third. We can take that decimal place that's right there, move it 1, 2, 3 places to the left. So we write that as 6.2 times 10 to the third. Gives you 6,200. Yep. So if you remember scientific notation, if I have a number written in scientific notation, if that's positive, it means to move the decimal 3 places to the right. And wherever there's blank spaces, you put zeros in. All right, how do you round numbers? I guess it depends on what number you're rounding to. So you decide what is the last digit you're going to keep. You leave that digit the same if the next digit to the right is less than 5. So you look at the next digit to the right. If that number to the right of the digit that you're rounding to is 5 or more, then you round that digit up, correct? So you increase that digit by 1 if the digit to the right of it is 5 or more. Okay, so round that to the nearest 10th. So how many decimal places is the nearest 10th? 1? Is this the 10th place right there? So what does that round to the nearest 10th? Yeah.
What is it, like number?
Mm-hmm. 7/10. So if you're rounding to the nearest 10th, this is the number you're rounding right here. And you look 1 digit to the right. If that number is 4 or below, you just truncate it, you just take it off. So since that number is 4, you just drop it. And it rounds to 0.7. Now, what if I had 0.78? It would round to 0.8. So again, this is the number I'm rounding to, the 10th place. If that is 5 or more, I add 1 to that. So 0.7 becomes, and I should use squiggly equals to be technical, because that is an approximation. And when we write it's approximately equal to, we typically write squiggly equals. Okay, round the following decimal to the nearest thousandth. So what's the thousandth place? It is the 7. That is the thousandth place. That is correct. So then what do you do? If you're rounding to the nearest thousandth, where do you look? At the 5. And what do you do to the 7 then? Turn the 7 to an 8. And then drop the rest. That is exactly correct. So it's 2, 4, 8. Is that correct? All right. Round the following decimal to the nearest hundredth. So what number is in the hundredths place? The 9. And what do? You look Where do you look? At the 8? So you round the 9. 67.3, very good. If you round the 9 up by adding 1, it becomes 10, so you have to round the 2 up also, don't you? 67.3, that's very messily written. I bet I could write that neater. Maybe. PowerPoint trying to help me. All right, very good, very good. How about this one? Round the following decimal to the nearest 10th. So what number is in the 10th place? The 9. So what are you going to do? 27.0. And the reason you have to write it as 27.0, you would round it to the nearest 10th. So you'd put the 27, but if you're rounding to the nearest 10th, they're going to want the 0 included. Yep. You're rounding to 3 significant digits in this case. So the 10th is actually significant. Nearest 100th, you would round that up to 9, and it would be 26.99 to the nearest 100th. To the nearest 1,000th, it would be what, 26.988 to the nearest 1,000th. So this is the nearest 100th. And here's the nearest 1,000th. All right. Let's look at section 2.3. So on last Wednesday, we started solving equations. And as you recall, to solve linear equations, which is what we're doing, is solving linear equations, we have a couple of 3 different things that we can do when we're solving linear equations. We can add or subtract anything we want from both sides of an equation. Anything. You can add or subtract anything you want from both sides of an equation. And then we can multiply and divide both sides of an equation by anything that is not 0. You can't multiply both sides of an equation by 0. You can't divide both sides of an equation by 0. You can't divide by 0, period. And you can remove parentheses and collect like terms as you can with any algebraic expression. So the 2 expressions on each side of the equation, if they contain parentheses, you remove them. If they contain like terms, you collect them. And then you can add or subtract anything you want from both sides. You can multiply or divide anything you want except 0. Okay, so we're going to look at the 2 special cases of solving linear equations, when you have no solution or when you have an infinite number of solutions. So everything we've looked at so far, we solved the equation and we got a result. So for example, if we solve this equation, if I solve that equation has a solution. There is a value for x that makes that true. So how do I find that x? Do I subtract 7 from both sides? So 3 minus 7, is that -4? When you add a positive and negative, you take the difference of the 2 numbers. The difference between 7 and 3 is 4. The bigger number is 7 and its sign is negative. So we make our difference negative. Okay, then what do? Divide by 2. And we get x is -2. And that is the correct solution. Because if I plug -2 back in, -2 times 2 is -4. -4 plus 7 is 3. So that equation has a solution. It's called a conditional equation. So an equation that has at least one solution, one value for x that makes it true, is called conditional. Now, we're going to look at a special case in just a second. If that equation is true no matter what x you plug in, it's called an identity. So that is not an identity because it's true only if x is equal to -2. But there are going to be equations that it doesn't matter what you plug in for x, it's going to be a true statement. And then there are equations that have no solutions. So when you try to solve them, you get a contradiction. You get something that doesn't make any sense. When that happens, that equation doesn't actually have a solution. So you have the case where an equation has one solution, it's conditional. It could have many solutions, that's conditional, but it's also called an identity. And then you have the instance where an equation has no solution, and that's called a contradiction. All right, let's determine if this equation is a conditional equation, an identity, or a contradiction. So if it has exactly one solution, it is conditional. And then we'll look at what happens if it's an identity or it's a contradiction. So how would you solve that? Combine like terms, exactly correct. We might as well, before we start trying to subtract that 2x from both sides, correct? So what's that going to be? 6x minus 11x.
Would be 17x.
No, you had it right the first time. No. You combine the two coefficients, 5, because you're taking the difference. But the 11 is bigger. So it's negative. So it's negative 5x. And when we combine x's, we still just have x's. We don't get x squares or anything like that. If we're combining using addition or subtraction, which is the case here, we're combining using subtraction, that doesn't change the variable at all. It could change the variable, it sure could. All right, so what do we get? And we get 2x plus 11, is that correct? Now what do you want to do? Subtract the 2x. So again, we're combining x's, so we're going to end up with an x. So we have -5, -2. What's that going to be? -7. If both numbers are negative, we just add the two numbers together and the result will be negative, correct? And then what do? Divide by -7. So we get what? X is -11/7. So our equation had one solution. If we replace x in the original equation with -11/7, it will make it a true statement. Yes.
So when you left it a fraction, you didn't divide 11 by -7. Is that just because you can't divide 11 by -7, or like?
I could only divide it and get a decimal approximation because -11/7 is not going to give me an exact value. So it depends on what the instructions in my lab math says. If it says write your answer as a reduced fraction, we're going to leave it alone. If it says give a decimal approximation to 3 decimal places, then you're going to divide it on your calculator and give a decimal approximation to it. So in my lab math, you'll notice you got blue writing on the problem. That's your instructions. So just read the instructions. Okay, this is a conditional equation because when we solved it, we got a solution. We got a single solution, so it's conditional. All right, how about this one? Let's solve this and let's determine if it's conditional, an identity, or a contradiction. So what would you do first? Okay, so what do you want to do with those parentheses? Okay, so what are we distributing? You got negative times negative gives you positive 25. So when I distribute that negative 5 across, the first term inside parentheses becomes negative 5x. The second term, the negative and the negative make it positive, and we get positive 25. So we have 11x minus 5x plus 25. How about on the right-hand side? Do you want to do anything over there? So 4x and 2x are like terms. So we add the coefficients and bring the x along for the ride. Okay, now what?
Here, 11x, or subtract 11x minus 5.
What do you get when you subtract 5x from 11x?
Negative 4. No.
6. 11 minus 5 is 6. So again, and the rules apply, positive and negative rules apply for everything. So if I have 11 and negative 5x, I subtract them. One's positive, one's negative, and I get 6. But 11's bigger and its sign is positive. So the result will be positive. So plus 25 plus 4x plus 25. Now what do you want to do?
Subtract the 4.
Oh, what have I done? I got a mistake here. What's my mistake?
Should it not be 6x?
Yes, ma'am. I think 4 plus 2 is 6.
I was like, I thought I wrote it down wrong.
No, that was just to see if you were awake. You are, you passed the test. Okay, now what do you want to do? So what's it mean then? So if I subtract 6x from both sides, I get 25 is 25. Or you notice that both sides of the equation were identical. 6x plus 25 on the left-hand side and 6x plus 25 on the right-hand side. What does it mean? No, it's actually the opposite. It means it's got every real number as a solution. So this is an identity because it doesn't matter what you plug in for x in the original equation, it will make the statement true. It doesn't matter. You can plug anything you want in for x and that original statement will be true. If you plug in 0, you get 25 equals 25. If you plug in 1, you get, well, I don't know what you get, but you get something. But both sides of the equation will always be identical. That's why it's called an identity. So no matter what you plug in for x, both sides are identical. So it's an identity. So what's the moral of this story? The moral of this story is you're solving an equation and you get something like this, where the left-hand side and the right-hand side are exactly the same value. What's that tell you? Oh, it's an identity and it has a solution set that contains all real numbers. So anything you plug in for x is going to work. Okay, how about this one? What you want to do? What am I distributing? Okay, so what do I get? 3x plus 9 equals, what do I get on the other side? What do I get?
3x plus 24.
Okay. Now what do you want to do?
subtract 2.
Subtract the 3x. Now you're puzzling about that because you're going to see what happens.
Yes, if your x's are the same, would you do the 9 and 24 first?
You could, but it doesn't matter. Because if you did the 9 and 24 first, you're still going to be subtracting 3x from both sides. What's that mean?
It does not.
So 9 doesn't equal 24. So this is no solution. This is a contradiction. And it's a contradiction because 9 doesn't equal 24. Would you agree? That is not true. So this is a contradiction, which means the original equation, there is no solution. There is nothing you can plug in, add 3 to it, multiply it by 3 on the left-hand side. On the right-hand side, add 8 to the same number and multiply it by 3. There's no number that's going to work there. Nothing will work. So this is a contradiction. Contradiction. So there is no solution to the equation. Okay, let's do a couple more. How about this one? What am I distributing?
First 5.
Okay, what do I get? Yep. Yep.
Also, that's I know.
It is an identity. Very good. Since the left-hand side and the right-hand side are identical, it's an identity. Very good. So if it's an identity, we should probably make note, if I can get back to the slide, that the solution is actually the set of all real numbers. Because I can plug anything in for X and it'll work. If I plug in 0, that works. If I plug in 1, that works. If I plug in 2, that works. It doesn't matter what I plug in for X, it will make the left-hand side and the right-hand side identical. Okay, how about that one? What do you want to do? Hey, what am I distributing? Plus 30? 6 times 5 is 30. Then what?
Do the 2 distribute 2.
And what do you get? 4 times 2 is 8.
8.
What's 8 plus 22? 30. It's an identity. Very good. One side is identical to the other. It's an identity. All right. Last problem in this section. Got B's. I don't care if I get B's instead of X's or Y's. That doesn't bother me. What do you want to do first? What am I distributing? 6V plus 6. Minus 2V. How about on the right-hand side? 4V plus 4 minus 5. Now what do you want to do?
Then you subtract 6 on both sides.
I can do something on the left-hand side before I try that. I got 2 V's over there, so I can combine them. What's 6V minus 2V? 4V. Very good. How about on the right-hand side?
4 minus
What's 4 minus 5? minus 1? Do you see a contradiction? Can you take 4b and add 6 and get 4b minus 1? Is that going to work? Now, if you continue to solve it, and believe me, I've been doing this a long time. And when students get to the point that they have 6 equals -1, they try to fix it. There's nothing to fix there. There is no solution to that equation. This is a contradiction. And it is not incorrect in any way, shape, or form to end up with an equation that's a contradiction. That's a fact. It's a contradiction. So this equation, the original equation, has no solution. There is nothing I can plug in for x that will make that a true statement, where it will make the right-hand side equivalent to the left-hand side. All right, are there any questions? All right, well, go take a break and we'll see you back here at 11.